powder diffraction. X-ray powder diffraction is a rapid and equivocal technique that used for phase and identification of crystalline material, and it can provide information on unit cell dimension, and the analyzed material is finely ground, homogenize, and the average bulk composition is unique. And this is a picture of XRD machine. And next, the application of XRD. Firstly, the characterization of crystalline material, and we can know the ratio of crystal to amorphous in a sample. And second, the identification of fine bright material minerals such as clays, and we can know the component contained in the sample. And third, the determination of unit cell dimension, and we can get the shape of unit cell. And lastly, the measurement of sample purity, and we can get the ratio of the component in the sample. And next, the X-ray diffraction pattern, and the image in the below is the XRD pattern, and the detector will move in a circle around the sample, and the detector position is recorded as 2 theta, and the detector records the number of X-ray observed at each angle 2 theta, and the X-ray intensity is recorded in counts.
Technique for identification for the unknown material. In most cases, it provides an ambiguous mineral definition. For the minimum sample version is required, and the XRD unit is widely available. For the limitation, it requires tens of the gram of material which must be ground into powder. For the mixed material, the detection limit is approximately 2% of the sample. For unit cell determination, indexing of patterns for non-isometric crystal system is complicated. Now, what I'm talking about, what is X-ray fluorescent XRF? An X-ray fluorescent spectrometer is an X-ray instrument used for routine, relatively non-destructive chemical analysis for rocks, minerals, sediments, and fluids. XRF cannot generally make analysis for small spot size, typically of EBB works 2 to 5 microns. So it's typically used for bulk analysis of large fraction of geological materials. It is relatively easy and low cost sample preparation, and the stability and ease of use the X-ray spectrometers make this XRF is most widely used method for the analysis of major and trace elements in rocks, mineral, and sediment. Now, for application of XRF, it's usually used in research in igneous, sedimentary, and metamorphic spectrology, soil survey, mining, and cement production, and ceramic and glass manufacturing, metallurgy, environmental studies, and petroleum industry, and also field analysis in geological and environmental studies. That's all.
Okay, I am going to explain how does XRF works. Okay, the sample is 200 X-ray. This is when X-ray is hit the electron from the inner shell. The electron will out of the atom, and then the electron from the outer shell will be filled up again by the electron from the higher energy shell. And then this radiation is characteristic for each element, like the pre-independence of the atom. Chemical bond, the intensity of radiation is proportional to the concentration of the element in the sample. As a result, a specific amount of energy is released. The energy of the emitted X-ray depends on the difference between the higher to the lower state. Therefore, the radiation also carries information about the atom. Okay, next, the strength and the limitation of the XRF. The strength of the XRF is particularly well suited for investigations that involve for biochemical analysis of major elements such as calcium, natrium, potassium, and so on. But chemical analysis of trace element, for limitation SRF, most commercially available instruments are very limited in their ability to precisely and accurately measure the abundance of the animal with proton number less than 11 is most natural earth material. SRF analysis cannot distinguish correlation among isotopes of an element, so these are routinely done with other instruments. What is energy dispersive X-ray spectroscopy, or we call it as EBS or EDS? Interaction of an electron beam with a sample target produces a variety of emission including X-ray, and then is used to separate the characteristic X-ray different elements into an energy spectrum. It is also used as elemental composition, mapping of the elements, mass thickness of thin films, and detect very small quantities. Together, these capabilities provide fundamental compositional information for a wide variety of materials.
This diagram is the result of EX or ES, and the typical ES spectrum is portrayed as a plot of X-ray counts, ES energy in KeV, where the energy is portrayed in the Y-axis, while the X-ray counts is portrayed in the X-axis. Energy peaks correspond to various elements in the sample, and the result of EX or ES depends on the abundance of the elements in the sample. So generally, they are narrow and readily resolved, but there are many elements that still yield multiple peaks. For example, we have Fe, which is iron, commonly shows strong Ka and Kb beta peaks. Elements in low abundance will generate X-ray peaks that may not be resolvable or probably less detectable from the background radiation. Okay, how does EX or EDX work? EDX systems are typically integrated with an SEM, which is the scanning e-microscope, or EPMA instrument, which is an electronic prescribing and medicine administration instrument. EDS system will include a sensitive X-ray detector, a liquid nitrogen for cooling, and also a software to collect and analyze energy spectra. The detector is mounted in the sample chamber of the main instrument at the end of the long arm, and also is cooled in liquid nitrogen. The most common detectors are made of SiLi crystals that operate at low voltages to improve sensitivity. But recent advances in detector technology make available so-called silicon drift detectors. Silicon drift detectors are detectors that are commonly used in XRF, EBS, and also electron microscopy. And the main characteristics of these detectors are they have high count rates and operate at liquid nitrogen cooling, and also they have high energy resolution. An EDS detector contains a crystal that absorbs the energy of incoming X-rays by ionization, yielding free electrons in the crystal that become conductive and produce electrical charge layers. The energy X-ray absorption, which is produced by the EDS detector, will convert the energy of the individual X-rays into electrical voltages of the proportional size. The electrical pulses correspond to the characteristic X-rays of the element. And for the first diagram, it's an EDS detector, which will show the nitrogen neutral core arm and detector tape that is mounted in the sample chamber, which is a large chamber up there. And then this is the cutaway diagram showing the construction of a typical EDS detector. We have the cold finger, which can cool down the whole system, and FET, which is the field effect transistor. And also we have the electron track, which will track the electrons and also be detected by the crystal.
Okay, hi, I'm Azfar. So we talk about strength and limitation of EDX and also ES. So the strength is when it's used in spot mode. A user can acquire a full elemental spectrum in only a few seconds. So the software makes it possible to readily identify the things. Which then ADS is a great survey tool to quickly identify element faces prior to doing quantitative analysis. For ADS, ISO can be used in a semi-quantitative mode to determine the chemical composition by peak high ratio relative to the standard. Then illumination is for gas because the wavelength is perceived, matter is more precise and capable of detecting the lower elemental abundance. So EDS is commonly used for actual chemical analysis. Although improvement in data resolution make EDS a relevant and precise alternative. And then EDS cannot detect the latest element, typically below the number of sodium for the latest included the window. So polymer-based steam windows allow for detection of light elements depending on the instrument and also the operating condition. Then SRT versus SRF. The both technique use an energy source and also detector. Both measure the response to action reacting with the substance, and both provide measurement to help identify the substance. And then SRT gives compound analysis, whereas SRF gives elemental analysis. So this one is the example. Okay, next. Okay, this is SRT versus EDS. Okay, SRT is used to identify the spatial arrangement of atoms in the crystalline phases. Then EDS is used for the chemical activation of elements and also near concentration. In SRT, X-rays often wavelengths are used to probe the structure of the material using the lattice or as a diffraction grating. Then in EDS, electrons from atom producing X-rays of penetration baseline. These X-rays are then detected to identify the element from which they were produced. For SRT, they need an X-ray source, while EDS need an electron source. Then we can interpret the phase resolution, the strain phase or stone effect content using SRT, while for EDS we can interpret the chemical composition, concentration gradient, Razali. Okay, thank you.